All right, I'm going to get started. Today we have a lo-fi version because I forgot the camera up in my office, which is way the hell up there. And I didn't feel like going back because I just noticed it as I was walking in, and then I'd be super late. So we're going to do everything today completely on the board, which is basically what I had planned anyway. So the only real difference is I'm going to be on this board instead of that one, and some of the things on slides aren't there. But today, we're just going to go through Kepler and Newton. There wasn't a reading today, which is good because I'm a little behind, but we're going to keep the reading okay on for Friday because I will start talking about magnitudes. I had another little lecture that I was going to sneak in here. I'm just going to sneak in only the essentials on Friday, so it'll work out. So today, does anybody have, before I jump right into the meat, does anybody have any questions or things that they want to talk about that's burning on their minds? Everybody's all right? So today I'm just going to do a bunch of math and the physics that goes behind that math. So this is all stuff that I want you guys to really understand. So all the stuff that I say today might be on a test, right? I like these derivations, and I think that the connections between the physics ideas are really very important, and that's what a lot of these derivations string together are connections between ideas. So the first thing I'm going to talk about is the connection between work and energy, which is a thing that several of you had asked about the last reading, so I'm still on the last reading a little bit, and then I'm going to get into Kepler and Newton. So, okay, where'd my eraser go? I need an eraser today. So work and energy. Work and energy. So energy and work are related to each other, and I'm only going to do this really fast. I'm just going to go through this one quick derivation because you've all seen work and energy before. I'm going to go through this one because it makes some very useful connections. So energy is a scalar property that objects have, and there are many kinds of energies. There's kinetic energy, and that's 1/2 mv squared, but there's also thermal energy, which I'll just call TE, and there's magnetic energy, 1/2 b squared, and there's gravitational energy, gm squared over r. There's all kinds of energies, but kinetic energy is the king of the energies, because kinetic energy is the thing that connects everything else together, because it connects the coordinates to the other stuff. The coordinates are the velocity. In all of physics, what we are really trying to find is r of t for something. We want to know how an object moves around, right? We want to know the position versus time of, say, a planet in an orbit, which is what we'll do today. Or a ball rolling down the hill, or a pendulum, or an electron in a penning trap, or whatever. We want to get r of t, and we get that from v of t. And we get v of t from a, from the acceleration of t. How do I get position from velocity? Integrate. And how do I get velocity from acceleration? Everybody? Integrate. Right? So that's fine, but how do I get acceleration? Force. So acceleration comes from force. Now this is the only thing that's not just a math relationship. This is where Newton had actual insight, is that force, which is like what I'm doing, is related to where I'm going to go. And it's related to where I'm going to go by acceleration. So energy is a property that says how things are moving around. The kinetic energy is the king of those because it relates the energy you have to the velocity, which relates back to the coordinates, which then relates to the force that you're experiencing. So all these things are kind of related to each other. So we know that work is minus, let's see, d work is minus f dot dx. Where work is a scalar, f is a vector, and dx is a vector. The dot product of those two things is the work that's done. And the energy, the change in energy, is the work done on a system. So if I do work on a system, I change its energy. If a system does work on me, the work is then of the opposite sign, but the energy changes on energy changes.
And is that the change in potential energy only?
Yeah. Or kinetic energy. Huh. That's what I'm going to show you right now. So we know that for some systems, F equals minus grad U. Now, this is very powerful because it turns something that looks like a vector, the force, into something that looks like a scalar, the potential. It is so much easier to deal with scalars than vectors. Vectors are a headache. They got a direction. There's 3 bits to them. You can't just like multiply. You can't multiply 2 vectors together, really. I mean, okay, you got a dot product. You can't divide 2 vectors unless you use really fancy math. But you can divide scalars and stuff. So this is really nice because it turns vectors into scalars. But it's not always true. So there are some forces that are not central forces like this, like the electric force, the magnetic force. So one thing we can show is that the potential for a gravitational system is just going to be the integral of the force dot dr. And there's 3 of those, because I've got 3 integrals to do. So if I integrate g m over r squared dr, I pick up a minus sign. Well, okay, I pick up a minus sign because of this minus sign, and then another minus sign, and then I pick up another minus sign from the integral, and I get minus g m over just r. The square turns into the 1, and that's just the integral, right? So you pick up a minus sign from the minus grad. So the potential energy, if the force is gm over r squared, the potential energy is just gm over r. Or if you want to be explicit, and I want to measure from r1 to r2, then I would write this as minus gm 1 over r2 minus 1 over r1. Does that make sense? So this is the change in kinetic, this is the change in gravitational potential energy as I go from one radius away from my planet to another. So the other side, so this is one potential energy, delta U is this. Or, because work is the same thing as the integral of f dot dr, that's just the same. I'm just doing this integral again. Now I'm going to treat it like a vector product, and I'm going to rewrite some things. So what is f? F is p dot. Okay, dot, I don't use it a lot because a lot of times I need to distinguish between full and partial derivatives. Dot over something means the full derivative with respect to time. Because we do that a lot, I just put a dot on top. You've probably seen this notation before, but I wanted to stop and make sure that I said it out loud. So this is the full derivative with respect to time. F equals p dot. Have you seen that before? That the force is the momentum derivative? Some no's, some yes. So F equals ma, right? That's equal to m times dv dt. If m doesn't depend on time, that's equal to d by dt of mv, which is just d by dt of the momentum, which is just p dot. This is maybe more fundamental than F equals ma. I'll stand on that side because I'm not transparent. Okay. Make sense, February? So F dot dr, can I see this side? Keep that alone. I teach in this room in the basement in GFDI, and it has these boards that slide around, and it's so awesome because I can just write stuff and then slide the board and get another one. This one I gotta move the camera. So, okay, so we're gonna come back to this. Work is minus F dot dr. Okay, so this is minus p dot, and what's r? Dr equals v dt. Does it make sense that I can say that? So d, the little d means it's a tiny infinitesimal piece, so it's just a tiny thing. So a tiny little bit of position change, pretend I'm wiggling infinitely small, is just a tiny little velocity change time, or is a velocity times a tiny little time interval. Does that make sense? So dr is just v dt. So f dot dr is just p dot v dt, right? Which is just minus m v dot v dt, just expanding out what momentum is. Now, I didn't necessarily need to use p dot for that, but I think it's important, so I wanted to make sure that I said that. Also, it's how the book does it. Where'd that minus f come from? What the hell are you doing there? Okay, this comes out because it doesn't depend on time. And this is dv dt times v. And what's that? That's, I can just integrate this by parts. Or I know how this works. Or this is just dv squared dt, and I get a 1/2 here. Okay. Does everybody follow that? Today's the day to stop me if you didn't follow what I said, right? So if I have dv dt times v, I can just integrate that once and call it 1/2 dv squared. Or alternatively, I can just take a derivative of this, and the 2 comes down and cancels that, and I'm left with my product rule, v times dv dt. Are we good on that? So this turns into just minus 1/2 mv squared. Or if I want to put specific limits, mv2 squared minus mv1 squared. Okay, did everybody follow that? Or did anybody does anybody want me to say that again? This relation, yes? All right. So, work is minus the integral of f dot dr. It's just the definition of work. Now I'm going to change both of these things and turn them into things that I can integrate. So this is equal to ma times v dt. v dt. Good? So dr is just v dt, so this is dr, or it is a velocity times a time interval. ma is just f dot, so I'm going to replace this a with v dot. And then rearrange a little bit, and I'm left with, m comes out, and I'm left with just the integral of v dot dv dt dt. So now there's several ways that you can approach doing this integral. The way that I do it is I just always see if I've got if I've got b times b dot, that's 1/2 b dot squared. It's just a thing that you remember. Or you can integrate by parts. How do I integrate by parts? Does anybody remember? I remember how to integrate by parts perfectly, and I'm a wizard at it. I heard about integration by parts, and I kind of forget about it, and that's probably a little dodgy. Yeah, that's okay. So let me tell you how integration by parts works. I'm going to go on the side. How many of you remember product rule? Product rule, remember a little bit more, right? Thank you. So integration by parts is just product rule backwards. So product rule is one of the most important things, and it's also one of the easiest things from calculus to remember. So if I've got d by dt of a times b, this is, I'm going to use the dot notation. A dot b plus a b dot, right? So now if I've got something that looks like a dot b, then I have this relationship between the derivative of the pair and the pair of derivatives, right? So here I've got something that looks like that. I've got v times v dot. So v dot plus v dot v equals 1/2 d by dt of v squared, 2 v's, right? Everybody got that? So there's just 2 of these, right? That's the same thing twice, so that I get out 1/2. So VV dot is just 1/2 V squared after I integrate it.
Sorry.
Yeah.
Can we, I know, I don't know if this sounds stupid, can we cancel out the dt's and end up with VdV and just integrate that? So we have V squared over 2.
Oh, yeah, so you could say, I can just say DAB equals DAB plus A dB. I can just say that. This is what you're talking about, is just canceling out the denominators, it's just dealing with the infinitesimals. This does what you want. Or you can go the other way. So, did that answer your question?
I feel like that made it more complicated.
Okay, forget that.
My head around it.
I'm going to need to come back to that in a second. So I'll come back to that idea in 1 second. So work is just 1/2 mv squared. And I think I'm probably going to assign this as a homework problem because I think that going through this process is really valuable. My wife is a piano teacher and I'm a physics teacher. And physics teachers and piano teachers approach things very differently. When you learn how to play a piano, you're given like exercises and you got to go grind through them, and you grind through the same piece over and over again. As a physics teacher, we just kind of fire hose information at you and hope that you catch it. So the things that I think are important, maybe we need to practice. So this one I think I'm going to do for homework.
I think it's like just the dot notation making it more.
Is that making it more confusing?
Yeah.
That's cool. It's going to get harder in a second. So. All right. So that's all I'm going to say about this one. I'm going to start with a different system. So if I lost you there, I'll pick you up in the next round because this is similar ideas, and we're going to reinforce these ideas. And the dot notation may throw people off, though I will try to be careful with that. So that's work and energy. So the one thing that we got out of this is energy is minus GM M over R, or it's 1/2 mv squared. Those are both very useful things, and they're related to each other. Okay, so now what we want to do is try to prove Kepler's laws. And not everybody followed all of those proofs in the book, because they're kind of gnarly. I mean, they're complicated. But I think they're very important, which is why I want to spend time on it. So let us begin. Let's recall what Kepler's 3 laws say. I'm going to write them over here because we don't need to see them on camera. So Kepler's first law is planets move on ellipses with the sun at one focus. And then 2, planets sweep out equal area in that ellipse for equal time. That was kind of weird. It's cool that it works, but it's weird. I'm going to do the proof first. And I get done and I'm like, oh, that's still weird. And then the last one is P in years squared, the period of an orbit, is equal to the semi-major axis in AU cubed. Okay. So everybody's seen these now. There's some homework problems on them. So let's talk about the second one first. So the first one is the first one the book does, and it makes the most sense to do that one first because the other 2 kind of need you to be on an ellipse, and we need some results from the first one. But the other 2 are a lot easier to digest. So I'm going to start with those because they connect the good bits of the physics. So equal area for equal time. Let us say, am I on the... So dA is a little tiny area element. So if I have my ellipse, my ellipses are always decidedly non-elliptical, but it doesn't really make a huge difference. So here's the prime focus, and here's the semi-major axis, and we're going to measure everything relative to the semi-major axis. So dA, if I start at r at one particular position, and I move to another position, dA is the area that I sweep out, covered by the ellipse. Right? So I am this planet, and I'm moving around like this. So what is dA? dA is just base times height. So that's just r dr d theta. So that's just a little blob in here, a little patch in here. Okay, the book doesn't put a square here, but I think there ought to be one there. Totally minor. But this has two infinitesimal things, a dr and a d theta. So dA squared is just a little element of area inside my blob. I haven't written anything useful down here. But what I can do is turn this into, is integrate once and get rid of the r so that I go from here to, so dA squared is a tiny little patch in here. I'm going to integrate this one time, dr, and this is going to turn into what? So the integral of r dr d theta, we're going to integrate over dr real quick. What's the integral of r? Is just 1/2 r squared, right? This is just 1/2 r squared d theta. Does everybody follow that bit? 1/2 r squared d theta. This is just the area of this little bit. You can think about this as 1/2 base times height too, right? Because this is d theta. This is the base, which is r d theta, because that's how triangles work. And then the height is going to be r. So we get 1/2 base r d theta times height r was 1/2 r squared d theta. So all I have is a little tiny triangle. Now, so I have dA equals 1/2 r squared d theta. I'm just going to divide both by dt. And now I have dA dt, which is what we're looking for, is 1/2 times r squared d theta dt. Does everybody follow me so far? You good? So this is the rate that area is swept out. So what we want to do is show that this is a constant. So that's pretty straightforward, because I know that r times d theta, here, actually, I'm going to use the theta dot out of principle now. So this is 1/2 r squared theta dot, because it's the time derivative of theta. I'm going to rewrite this as 1/2 r times r theta dot. And this quantity, r theta dot, rv, that's v theta. That's the velocity in that direction. Why is that? For the same reason that, because, again, of triangles. So if I've got some angle here, the length here is r theta. So if this is changing with some velocity, then this is changing with some velocity. That's the same thing times r. That makes sense? So v theta is that. Now, what is rv theta? Rv theta is just the angular momentum over the mass. This is just the angular momentum over the mass. I'm going to turn that into a mu in a second, but I don't need to right now. How do I see that? Because what is angular momentum? Actually, let's talk about angular momentum for a second. So, what do you remember about angular momentum? So yeah, what do you remember about angular momentum?
The figure skater pulls her arms and goes really fast.
How come?
Because conservation of angular momentum.
And what is that? What is the thing that changes?
Radius.
Radius. And angular momentum is? No, give me a formula.
Oh, VR sine. Oh wait, sorry.
Not VR.
VN. No.
Not
VNR and VR.
R cross V times N. Or I omega, but I'm not going to worry about omegas and stuff. I'm going to do this. And the sine theta, it comes from this cross product. So the way to remember it, the thing to remember is angular momentum is r cross v, where this cross is the vector cross product. What's that? Okay, so I've got an axis. Angular momentum is always relative to an axis. And I got some distance from that axis. That's a distance r. And I've got some velocity that's going in some goofy ass direction, right? I don't care which direction it is. Maybe this isn't in the plane of the board. Maybe this is going off. I don't care how you deproject this. It's at some weird angle, right? So this is v and this is r. R cross v is the vector cross product, is the vector product between these two things, and it is in magnitude equal to the magnitude of r times the magnitude of v times the sine of the angle between r and v. This is where that sign comes from. So if I think about this like geometry, I always got to write SOHCAHTOA down because I can never remember it. And I've been using SOHCAHTOA for like 40 years now. So anyway, so sine is opposite of our hypotenuse. So this one, so if I've got some angle here, the sine of it gives you the perpendicular component. So this is v, this is r. I'm going to break my velocity into a vr and a v theta. A radial velocity and a theta velocity. Okay, this actually should be coming out at you the way I drew it, right? It's not along the axis, it's coming out perpendicular to the axis. So if I just think about v theta and not, okay, r cross v is r times v times the sine of the angle, or I could just say r v theta, because v theta already takes care of that. Does that make sense? So I can just simply call r v theta the angular momentum per unit mass. Okay, well, what's that? What is L? I didn't do that part. Let's talk about L for a second. And actually, let's set the whole thing up. So here, what I've shown is that so this is dA dt. dA dt, the rate that you're sweeping out of area, is just equal to the angular momentum, really just because of this v theta, right? The v theta is how fast you're moving around, and r is how far away you are. Both of these things change in time, right? How far away you are from the planet and your velocity both change in time a significant amount. And they're related to the specific angular momentum. So now let's talk about the specific angular momentum for a second. L, actually, let's actually set up the system now. So I showed the second one, but let's talk about what we're doing a little bit better now. So here on the setup, really stop me if you don't get what I'm talking about, because if I lose you, you will be lost. Okay, so I have two particles, two objects. Let's call them planets. They'll be planets for now, but they might be black holes, who knows? Or galaxies, or stranded astronauts in the middle of space, only feeling their own gravity. That's never going to happen. You're always going to feel something's right. Okay, say you've got two black holes. They're in orbit with each other. What are the properties that these black holes have? They have M1 and M2, two masses. They have positions in space, R1 and R2. They have velocities, V1 and V2. They also have accelerations, and the derivative of the acceleration, which is called the jerk, and derivatives of that, and all of those others. Right? But these are the important ones. So R1 and R2 are relative to some point. Let's call them R1 and R2 prime for a second. Because prime is harder to write, and I'm going to get rid of this whole variable in just a second. So R1 and R2 are the positions of these objects, and those positions can be relative to whatever coordinate system you need, right? So let's say that we'll tie everything to the center of the galaxy for now. which is 8 kiloparsecs. So these two planets have R1 and R2, and they have positions R1 prime and R2 prime that are relative to I don't know what, but I don't really care. Because the only thing that really matters is the relative separation and how fast the system is going as a whole, which I don't actually care about. So that part I don't care about, and I only really care about the relative difference between the two objects. Now the book spends a little bit of time and says, okay, if I deal with the center of mass is the mass-weighted average position, and it's an incredibly important quantity. So the center of mass is going to be m1 times r1 plus m2 times r2 over m1 plus r1. So this is m1 plus m2. So you see what we've done? We've multiplied by m1 times r1 and m2 times r2, and then divided by the sum. This is like a weighted position average, like this is where the stuff all is. Right? Now the book goes through, and I'm not going to actually do the math, but what the book shows is that r dot is 0.
So that's the derivative?
Yeah, this is the time derivative of the position of the center of mass. And it's 0. So the center of mass of a thing in free space will keep moving on whatever path it's got, right? So this doesn't say that the velocity, oh sorry, I gotta say the right thing. This is r double dot. What's r double dot?
Acceleration.
Acceleration. So this says the acceleration is 0. The velocity may not be 0. Like the velocity of the Earth-Sun system is not 0. We're traveling around the galaxy at 270 kilometers a second. It's really fast, so we're traveling really fast. The velocity is large, but the derivative is small, so this thing's not going to horse around. So we can treat this as an inertial reference frame and get rid of the velocity and move the position to where this quantity is 0. Right? So we're going to introduce, oh, this should be prime, prime, prime. This is prime, the center of mass. So we're going to change to a coordinate system where R1 and R2 of my two planets are all relative to the center of mass. So we'll say that R1 is R1 prime minus R, and R2 is R2 prime minus R. Oh, that should be prime because that's the center of mass. So we just take off the center of mass, and everything works just fine. So we're just fine by doing this. Okay, so now what I want to do is really deal with just R, which is R2 minus R1.
Question?
Yeah.
What does prime actually mean in this case?
This one,
Yeah, just like primes you have.
it means this one. It just means that it doesn't have any flavor to it. It's just decoration. It's just a hat. It's just a color. I mean, I could use a letter. I could use another letter. I could call this Q. I call these guys Q. It doesn't matter. But I need one variable to describe its position relative to the center of the galaxy.
Oh, so it's related but different. Okay.
Yeah, so it's related but different. That's a very good question, so I appreciate that. So it's just a decoration to say that this R is different. It's going to be different from this R, but they are going to be related. So now in other contexts, and that's a very important question, because in other contexts, prime might be full derivative. So please ask the questions when they come up. So if I write down R2 is R2 prime minus R prime, and R1 and R1 is R1 minus R prime. So I just move my positions relative to the center of mass. Then what I can show is that R equals M1, same mass. We haven't transferred the masses, times R1, which is now this shifted one, plus M2 R2 over M1 plus R1 equals 0. And you can show that R1 equals minus M2 over m over mu times r. Now here r is the difference. It's their relative coordinates. Yeah.
And what is reduced mass?
I'll tell you in a second. So, and then R2 is M1 over mu times R, where mu is M1 plus M1 M2 over M1 plus M2, or 1 over M1 plus 1 over M2 to the minus 1. It's the harmonic mean, but that doesn't actually matter. What it is a stunt to make this work. That's really what I care about. But so what we see is now we've got these reduced coordinate systems, and now I've got an equivalent V1 and V2, which is R1 dot and R2 dot. Right? Now the derivative of R1 dot is the same as my original coordinate because I just changed it by a constant.
And so R1 is negative, but R2 is positive? Or has a negative direction?
Yeah. That works too.
So either way, they're just opposite signs.
Just opposite signs because I'm adding them up and it's got to be 0, so I can multiply it by 0 by minus 1, and it doesn't matter. I don't need this. I need this.
And the denominator for big R is supposed to be M1 plus R1?
Oh no, M1 plus M2.
M2, okay.
I have no idea. That's the second time I've done that. I don't know why I'm doing that.
I
That's
thought
a
that made
weird
more sense. I was
squirrel
just
brain. My brain is a team of 57 squirrels all trying to work together. I'm not doing a very good job. So V1 is R1 dot and R2 dot. So is everybody happy with what I've done? So now I've got two planets. I've got the center of mass, which we can pretend doesn't move, because it doesn't move. Turn the camera. And I've got R1 and R2, and you'll see they've got to be in opposites. They've got to have opposite signs because they're pointing in opposite directions. And they have different sizes, but they are materially opposite of each other. And the important vector is R. Now, which direction does R point? It doesn't matter. It's not gonna matter. R is just the difference between these 2 points, between the two masses. Now, okay, let's talk about energy. The energy for this new system, so the energy initially is 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. Okay, so this is the energy of the system that I wrote initially. The kinetic energy of the system that I wrote initially. Oh, what am I missing? This is the kinetic energy. What's the other energy? It's the gravity energy. Minus G M1 M2 over R1 prime minus R2 prime. So this is the kinetic energy of the first system that's relative to the center of the galaxy or whatever. Or whatever coordinates you care about. Now, when we move to this center of mass system, the velocity gets replaced by R1 dot and R2 dot, and this difference gets replaced by R. And if we do the algebra, and I'm not going to do the algebra, watch me do algebra, it's boring. If I take this R1 and this R2, and I take their derivatives and I plug them into here, and I take the total mass, M, M1, M2 is what? M1, M2 is just mu times big M. You see that? Because M1, M2 is, because mu is M1, M2 over M1 plus M2, and big M is M1 plus M2. So this is the total mass. This is the reduced mass. It's like a harmonic average of this stuff. And M1, M2 is just mu M, so that's great. So you do a little bit of algebra, and you're left with this is equal to 1/2 mu V squared minus G big M mu over R. Okay, what have I done now? I've gotten rid of a whole term. Sweet. This denominator is now only one variable instead of two variables. Sweet. But what I've done is a completely equivalent. I'm gonna make you do this for homework. This is one of the homeworks is just show this. Yeah.
And so what are V1, V2, and V?
So V is R dot, is the derivative of the displacement vector. It's the relative velocity. Thank you. Mu is the reduced mass, M is the total mass, and R is the separation. Is that all the things that you asked about?
Yeah.
So how do I interpret this? Okay, so what I've done is mathematical, kind of, but also intuitive. So I've got two objects that are orbiting each other, and that gives me 6 variables, 2 of which are vectors. I don't like that, that's horrible. But I don't need all that information because 6 variables, 2 of which are vectors, describes the orientation in total space as well. I don't need any of that. So we can get rid of a whole bunch of stuff because I don't care how I'm moving relative to the center of mass, so we can get rid of that. And the only thing that I care about is the relative separation, so we get rid of that variable too. So now I've got an equation that just has V's and R's in it. Yeah.
Is that, next to V, is that the total mass, or is that
This is mu.
reduced mass? So why? Because I thought it was just the 1 plus M2 because you factor out the...
It's neat how that works. It doesn't quite factor out like that.
Okay.
Because I've got a mu on these guys. So this is R1. R1 is M2 over mu times the separation vector.
It's just no intermediate steps, but that's what it comes out to?
Yeah.
Okay.
I mean, yeah, there's intermediate steps in here that you guys will do. Watching me do it is not interesting. I just want to get to the end point, right? So the algebra is you plug in this and this into here, and then this comes out. You can do it in your head once you've done it already, but. So how do we interpret this? This is the kinetic energy of something moving with the reduced mass. And this is an object with that reduced mass orbiting something with the total mass. So I've taken this complicated system and turned it into one thing orbiting something that's fixed. That make sense? Yeah.
Will there ever be a case where we need to also worry about rotational energy? Like if we have instead of just planets, we have asymmetric asteroids or something like that.
There are other things that you also have to worry about if you've got blobby objects, like their tidal torques. But the center of motion, say I'm trying to deal with what are some real floppy things? Simone Biles and 80 pounds of towels, okay, orbiting each other. Okay, Simone Biles flops around a lot and spins like crazy, but when she moves, when she's on that, what do you call it, the bouncy thing? The vault. The vault, yeah. When she's on the vault, she moves like crazy, but what does her center of mass do? Her center of mass moves on a perfect parabola. And it's a very simple parabola. It's well described by, right? Her center of mass is very simple. Everything else is complicated, flopping around all over the place. She doesn't flop around, she's very tight. But the center of mass is what matters. So if you had something complicated, the way you would do it is break it into 2 problems. One, which is the orbital dynamics of the center of mass, which is exactly what we're talking about here. And the second would be their internal their internal torques. So you would break it into 2 problems, but the first step would look exactly like this. That's a very good question. Other questions? Good so far? How am I doing? Oh man, I only got to setting it up. Still not sure how long 50 minutes is. Okay, definitely don't do the reading for Friday. I'm not getting to that stuff on Friday. So I'll postpone the reading. So okay, I got 5 more minutes and now I'm gonna get into something a little bit newer. So the next bit is the important bit. All of these derivations are all about angular momentum conservation. So let's look at what the angular momentum is for this system too. So the angular momentum system is going to be m1 r1 cross v1, let's put primes on these guys, plus m2 r2 prime cross v2 prime. But that is just definition. I'm just putting the things that I have into the definition engine and turning the crank, and out comes the angular momentum. Now if I plug in, and all you have to do is solve R1, all you have to do is plug these guys into here and do a little bit of algebra, which again is boring to watch me do. I have the angular momentum of these two things. Now we've got this reduced system. The angular momentum becomes u times r cross v, where this is now the difference, or the coordinate relative to the total mass. This is the reduced mass, and that's it. That's all there is now. And you'll see, I'll make you do it so that you put your hands on walking through this process. But the angular momentum is just the reduced mass orbiting the velocity. So that works out just fine. So now what is the,
You get the whole system.
the whole system, both planets, the total angular momentum is just this. So L dot, let's think about what the time derivative of L dot is. So this is going to be, let's move the mu over here. All right. So this is going to be, okay, cross product, I'm going to differentiate this thing. It behaves just like product rule. So this is R cross V dot plus R dot cross V. Everybody good there? Shake your head violently if you don't believe
Is
them.
V just the same as R dot?
Yes. So what does that say about this term?
It's just R dot squared.
It's just v cross v, which is 0.
I got two answers. Someone else say something. It's 0. Because if I've got V cross V, this is V times the sine of the angle, and the angle between these two vectors is,
0.
and the sine of 0 is 0. So this guy goes away. Yay. Sweet. So that's 0. And R cross V dot, this is R cross, sorry, my brain is trying to make me skip a step, but I can't do that. This is R hat dot. Does that make sense? So
time
V
of r times r hat.
yes. So this is the time derivative of r times r hat. So this is the unit vector times its quantity, taking the time derivative of that whole thing. Does that make sense? Which equals R cross product rule, R dot R hat plus R hat dot. So this R hat dot you can see as 1/2 R hat squared dot. Same thing. A times A dot is 1/2 A dot squared. A squared dot. And the time derivative of this, what is R hat squared? What is the magnitude of R hat squared? 1. Because R hat's the unit vector. So when I square it, I get 1. So the time derivative of this term is 0. And the time derivative of this term is another vector crossed with itself. And so that's 0. So dl dt is 0.
Can you repeat that? Which term? 0.
Everything's 0. For 3 different reasons. but everything's 0. So it's 0 because r dot is v and r cross v is itself is 0. The v dot turns into two terms. It turns into an r dot r hat and an r hat on an r hat dot squared. R hat dot is 0, and r dot r cross r hat is 0 because the vectors are the same. Follow? It's a homework problem, so you don't need to grok that now. It's a homework problem. Spend a minute with it, and then we'll talk about it in office hours. And that is it for me for today. I got through angular momentum.
Oh, so there's no change in angular momentum. That's a
Yes. So the important bit is angular momentum is a conserved quantity. It doesn't change at all.
okay.
That's the important takeaway.
That's, okay. So I get the important part.
Yeah.